Okay, welcome to this second part of the non-convex clustering lecture. Now we have discussed a method to actually derive non-convex clusters by means of k-means. K-means actually just computes convex clusters, but with the kernel trick we are able to compute also non-convex clusters by applying k-means in a transformation of the feature space. And we have also seen that this works sometimes, but in general, this is not very robust and is also quite computationally expensive. So what we're discussing now is a graph representation of our data and how we can cluster the data in this case. So first of all, let's have a look at our informal problem definition of the task we are looking at now. The thing is that a similarity matrix can also be interpreted as a representation of a graph. And how does that go? So first of all, we say every data point is a node. So you see here the plot of the points, and now they are interpreted as nodes in a graph. And the weight of an edge reflects the similarity between connected nodes. For example, we could use as similarity measurement the epsilon neighborhood. So this is related to the RBF kernel, only that we have here these discrete values, right? So we have either 1 or 0. So it's a 1 if the data points are below the similarity threshold of epsilon, and 0 otherwise. So that means that we draw here for every point one circle with radius epsilon, and we connect this one point here to every other point which is within this circle. So it's a bit similar to RBF, only that here, we do not represent, for example, edges which have only low similarity, but in RBF kernel, every edge was actually existing, so to speak. So here we get a more sparse connection of our data in its graph representation. Or another option is to represent the similarities by means of k-nearest neighbors. So k-nearest neighbors generally is directed, right? So if one point is in the k-nearest neighbors of another point, then it doesn't mean that this also is the case vice versa, right? So then we have to make the similarity matrix symmetric, because similarities are supposed to be symmetric. So we have here this nearest neighbor matrix N, which indicates if our point with index I is a k-nearest neighbor of the point with index J. And then we use here the mean values, basically. So we add here N and N transposed, and then we divide it by 1/2. So then we have that the similarity matrix W can attain values of 0 or 1/2 or 1, and it's in the n times n dimensional space. Okay, so what is here our problem definition? How do we define our clustering based on a graph representation of the data? Well, first of all, let's talk a bit about the representation of a graph by its adjacency matrix. So this is the matrix W. Every column represents one node, and every row also represents one node. And then here the entry W12 represents the weight of the edge between node 1 and node 2. So node 1 is here and node 2 is here, and then we have a 6. And there are no self loops in this graph, so every weight between the edges from one node to itself is equal to 0. And then this is how you denote your graph by a weighted adjacency matrix, or how you compute then the graph based on the weighted adjacency matrix. So you can just go through this piece by piece. So for example, here the connection from 1 to 3 is 0 because there is no edge, right? And it has to be symmetric, because if there's no edge, then this holds also for the edge from 3 to 1. So if we have a look here at the edge from 3 to 1, then there is also a 0. So this is here a symmetric matrix. The weighted adjacency matrix, there are zeros on the diagonal, and you can mirror it, right? You can mirror all of the elements, and then they're the same. So this is a symmetric matrix. And computing now the similarity within a cluster, as we have done it a bit for this for the build-up for kernel k-means, means then to multiply the cluster indicator vector y with the similarity matrix times y again. So what you can do here is you use this example. It's the same graph as we had before, as we had here. So here is the similarity matrix denoted. And then we have here now the cluster indicator vector of the nodes 1, 2, and 5, right? So this is this cluster here. And now if you compute y as transpose times w times ys, then you get here 2 times 5 plus 6 plus 7. And this is actually the sum of all the edges which are connecting the points within this cluster here, right? So here we have 6, 7, 5, and then this times 2 because we have 2 directions. So this is then the result we get. And now we can state the similarity function we have already explored for kernel k-means. This trace objective, if we compute this here again with respect to our notation of sets, then we see here that we sum the similarities or the edge weights which represent the similarities of point j and I. So here is the sum of all edges within one cluster. But for this graph representation, there's also one other way to compute a measurement for clusters, and this is the cut. So the idea is here, we have here again the cluster consisting of the nodes 1 to 5. So this is here indicated by the vector ys. And now if we cut this cluster here out, what kind of edges would we actually have to cut? Well, it would be this edge here, right, with the weight of 1. And it would be this edge with the weight of an 8, and it would be this edge with the weight of 4. So the cut would be here equal to this term 1 plus 8 plus 4, and we can actually compute this by computing the adjacency matrix W with the cluster indicator vector from the left and the indicator vector of all nodes except for those in the cluster from the right. So as an exercise, I would again recommend for you to do this by hand once. And this way we can also compute another function which can be used as a quality measure for a cluster, and this is the cut. So here we have then the trace from all the points which are not in the cluster times the similarity matrix W times the indicator matrix of each cluster. And then we normalize again here with the number of points within one cluster by this Y matrix Y transpose times Y. And then again, we can compute this also by means of our representation of clusters by sets. And then you see here that we sum up here all the edge weights which are between cluster CS, and the index I encompasses all indices which are not within cluster S. So this is here then the cut, the sum of all edges which we would have to cut if we cut cluster S, and then we normalize here with the number of points within cluster CS. So we have here two ways now to compute our cluster quality, and this is either maximum sterility or minimum cut. And they're all equally good in principle, so you can either define your clustering to maximize the sum of weights within clusters or to minimize the sum of weights between clusters. And yeah, let's state this also now as two different objectives. At the one hand, we have the maximum similarity graph clustering, where we are given a graph which is indicated by our adjacency matrix W and the number of clusters. And the task is to find clusters indicated by the matrix Y, which maximize the similarity of points within a cluster. So this is here then this objective. Or we can also go the other way, so we can search for those clusters which actually minimize the cut of each cluster. So given a graph indicated by a similarity matrix W or adjacency matrix, you can call it as you like, and the number of clusters R, and the task is to find clusters indicated by our matrix Y, which minimize now the cut. So this is here then this objective, as we have discussed it before. Okay, how do we optimize this? Well, first of all, we need to have a look now at the degree matrix, because the degree matrix is important if we talk about graph clustering. So the degree matrix is a diagonal matrix. You see here IW is the notation here for the degree matrix of our similarity matrix W. And for every node, it denotes the degree of the node. So here we have node 1, for example, and the degree is the sum of all edges which are connected to that node. So the degree of node 1, here we have the edges with the weight of 6 and an edge with the weight of 5. So the degree is 5 plus 6, which is 11. And for node 2, we have here a weight of 6 plus 7 plus 1. And this is then equal to 14. And this is then how we go on and go on, go on. And why is this interesting? Well, this similarity here, right? So this was ys transpose times w times ys is the similarity of all nodes within the set indicated by ys. And this is equal to the sum of all degrees within the set of ys, if and only if ys indicates a connected component. So that means we can here compute connected components by a requirement which is equivalent to this term here. So this is derivable from here. So we subtract here now ys transpose times the degree matrix times ys. And then, we can actually, with distributivity, compute that this is equal to this formula here. And this matrix is called the Laplacian. This is the graph Laplacian. Another thing which is interesting for the graph Laplacian is that it enables us to conclude an equivalence between the minimum cut and the maximum similarity clustering objectives. So actually minimum cut and maximum similarity objectives are the same, only on different adjacency matrices. So given a symmetric similarity matrix W, our degree matrix IW, and the graph Laplacian, then the following objectives are equivalent. So now here the minimization of the cut from our similarity matrix W is equal to maximizing the similarity on the negative graph Laplacian. And this maximum similarity objective is quite related to our kernel k-means objective. So it's actually the same objective using minus L as kernel matrix, but minus L is in fact actually not a kernel matrix because it's negative semi-definite. It's not positive semi-definite, which had to be the case for our kernel matrix. So minus L does in general not have a symmetric decomposition. That is here the problem. So this means that we cannot apply just kernel k-means here on minus L. But this is also not so much of a problem, because what we want to do now is we want to use a truncated eigendecomposition. And therefore it becomes important to know what are the interesting eigenvectors. Well, one of the things is that the graph Laplacian has this connection between connected components and its eigenvectors. So given a graph indicated by the symmetric matrix W, then the indicator matrix of the connected components are eigenvectors of the Laplacian to the smallest eigenvalue 0. And why is that? Well, for every connected component, there exists an order of columns and rows such that W has a block diagonal form. For example, we have here C connected components, and you see here then that these C connected components can be denoted here as the first block. And then we have here this block diagonal form, and the vector V is here now this indicator of this connected component. So it has here C1s. And then if we multiply here now this matrix, this block diagonal matrix with our vector V, then what we get is here, for example, we just add W11 plus and so on W1C. This can be also stated as the absolute value of W1 because W is non-negative. And this is then again equal to IW times V, where IW has actually on the diagonal these values here. And if we subtract here now from this equation WV, then we have here what we actually wanted to show. So that 0 is equal to IW minus W times V, and 0 is then equal to 0 times V. So V is an eigenvector with eigenvalue 0. Okay, so the eigenvectors to the eigenvalue 0 are here now actually not interesting because they indicate the connected components. What we do not want is to cluster based on connected components in a graph. And that is because clustering on connected components is very sensitive to noise. But this property here of the eigendecomposition will become important for spectral clustering. And spectral clustering is the standard method to solve the minimum cut objective. Now, the idea of spectral clustering is basically the same as of kernel k-means with few alterations. So, for example, instead of using the full eigendecomposition, spectral clustering uses only the first R meaningful eigenvectors, which are not indicating the connected component. So, the pseudocode here for spectral clustering is given as follows. Well, first of all, we have here this requirement that the parameters of the similarity measure should be chosen such that the graph is connected. And then spectral clustering is defined for a given rank, so the number of clusters, our data matrix D, and a similarity measure sim. And then we compute the similarity matrix W, or you could also say it's the weighted adjacency matrix for our data represented as a graph. And then we compute the graph Laplacian L. And then we compute here a truncated eigendecomposition of L. And V is here, in this case, an n times r plus 1 dimensional matrix. So in kernel k-means this was an n times n dimensional matrix, and here we have just r plus 1 columns. So this is a big relief computationally. And then we throw away the first eigenvector, which denotes our connected component. And this gives us here the matrix A. And then we compute k-means on A, and then we get here our clustering. This is spectral clustering. And yeah, it works. So what is done in practice often is that the weighted adjacency matrix is normalized. So then we normalize with the degree matrix from the left and the right. So this result here is derived with the similarity normalized matrix. And then we get here this clustering. And let's have a look at the most important slide of this lecture. So the following objectives are equivalent. Here we have now our k-means objectives as before, but we also have this objective here to maximize the trace. This k-means objective here is the sparkling start for kernel methods. And the idea was here that we replace D times D transposed with a kernel matrix K. And then we derived our kernel k-means method by the symmetric decomposition. So we'd say k is equal to A times A transposed in this case, and then we have not our representation by means of the data, but by these symmetric factor matrices A. And because this method was already kind of working for some cases, but in general, what is done is we apply spectral clustering, and this was relying on the same idea, only that we did not have our kernel matrix, but we had here minus L for the graph Laplacian, and the objective when we used the graph Laplacian had an interpretation as minimizing the cut of the clusters in our graph representation. And here we had then our truncated eigendecomposition. So here we use a truncated eigendecomposition where we actually neglect the eigenvalues. And I denote this here with VR, taking our interesting or important eigenvectors. Okay, I know this is probably a lot. But what I just said, what is the main takeaway point for the most important slide of this lecture with these various objectives? If you can follow this, if you can somehow understand this, then this is what I want you to take away from this lecture. I also prepared a notebook and discussed some aspects therewith, so I'll see you then.